Okay, so good evening, everyone. Welcome to the ninth live session for the course Concrete Technology offered by NPTEL. I am Harshit Agrawal, a PMRF scholar from the Department of Civil Engineering, IIT Bombay, and I will be conducting weekly live session for this course for the entire course duration. So, first of all, for those who have joined the session for the first time, these are doubt clearing and interactive sessions which are held every Tuesday from 6 p.m. to 8 p.m. till the course runs. And during the session, we interact by answering to the questions that I will ask in the chat box, by posting your questions in the chat box, or by raising hand, unmuting, and asking your queries. Apart from the class, you always use the discussion forum of the course for clearing your doubts. And attending these sessions regularly will help you to answer the graded assignments easily and will help you to further understand complex topics holistically. So, in today's session, we'll first revisit the last session that was for week 8 content in a quick recap manner, and then we'll cover the things that was covered in the week 9 content. The week, I guess there's some disturbance. Ankan, please mute yourself. No? Yes. So, in the week 9 content that we'll discuss today, we will continue first our discussion on mechanical properties of concrete that was left over from the last week, and then we'll start with the actual content that was covered in the week 9 sessions. Okay, so this session is divided into following sections. We'll first talk about elastic modulus of concrete, then fatigue in concrete, then bond strength of concrete, creep in concrete, and shrinkage in concrete. And finally, we'll conclude the session. In between, we'll have some objective questions, like around 15 to 20 questions in total, and some numerical questions that will help you to challenge your understanding of the concepts that we will discuss. And at the end, I will try to address any other queries if there are still left post discussion. So, in the last week, we concluded the eighth week of the course where we talked about strength of concrete. We discussed why concrete has higher compressive strength than tensile strength and saw two theories that supports this discussion. One was based on CSH bonding, and other was based on the crack propagation in concrete. We saw how cracking pattern differ inside and outside concrete. For inside concrete, we saw how cracks and pores affect the strength of concrete by discussing about Griffith's theory and Power's law. We answered why crack propagates through ITZ, the interfacial transition zone, and since ITZ has a higher proportion of porosity than bulk cement, uh, it is more prone to cracking that we have understood. Then we talked about how cement paste can affect the concrete strength through this flow chart. So we have type of cement, age of cement paste, curing condition, and admixture used, which can affect the degree of hydration and the gel structure and composition. These two properties, along with the W by C ratio, can affect the porosity of concrete, and finally can affect the strength of the paste, or we can say in turn strength of the concrete. Similarly, how aggregates affect the paste aggregate bond and directly concrete also we saw through this flow chart. So the surface roughness of aggregate and the chemical composition, they can affect the paste aggregate bond, which can affect the strength of the paste, strength of the concrete, I should say here. And aggregate proportion, particle size, and modulus of elasticity can also affect the strength of the concrete. Apart from the effect of concreting element on compressive strength, we saw how testing setup and sample dimension can affect the concrete strength. So in this, we saw how different specific requirements are there in IES 516 for compressive strength testing, like sample shape, dimension, loading rate, moisture condition, and capping material. And for each, we understood how they affect the compressive strength value. Finally, we talked about tensile strength of concrete, different ways in which tensile strength of concrete is determined. That was like using split tensile testing and modulus of rupture testing. So this was all from the previous session. Now, the next part is the elastic modulus of concrete. So, what is this elastic modulus, or we can say modulus of elasticity? So, simply saying, it is the ratio of applied stress to the corresponding strain that is generated when load is applied on the concrete. Okay, and this defines the ability of concrete to withstand deformation due to the applied stress or load. Okay, so for a stiff concrete, it will deform less under a certain applied stress. Okay, now it is observed that concrete shows a non-linear elastic behavior when it is subjected to some any load. Okay, first of all, what does this non-linear inelastic behavior mean? So non-linear behavior means that strain is not linearly increasing with stress. Like if you see in the figure, the rate of increase of strain is in low side at the initial stress level, it is low. Okay, and slowly as the stress is increasing, the strain rate is also increasing. So this is a non-linear behavior. And inelastic means that if the applied stress is removed, then concrete won't regain its original shape back, it will retain some deformation. So that defines inelastic behavior. Okay, now why concrete shows non-linear inelastic behavior? It is because of the way crack propagates in concrete. So at initial lower stress level of like 30% of the ultimate load, microcrack starts to form at the ITZ that we have seen. Now the curve already starts to deviate in this region. It's like suppose this is up to 30% ultimate load. Okay, so in this region you can see the curve have already started to deviate from the straight line, indicating that the non-linearity will achieve even before I have reached the peak load. Okay, now if I will remove the load from this point, what I will see that a small permanent strain remains, but most of the deformation is recovered. That is partially elastic. Here, if the load is still 30% only, then there will be some partial recovery of deformation that I can see. Now, if I go to the stress level of up to near this ultimate load, what will happen? The micro cracks will widen and new ones will be formed, which will show non-linear behavior. The stress redistribution continuously will occur around the crack, and if the load is removed, there is a hysteresis effect, meaning that the energy is dissipated due to the internal damage, which will appear as a permanent strain. So, suppose I have till here I saw that if I will remove load, I will achieve some partial recovery. However, if I will go up till this maximum stress level and if I will remove load, then in this way the strain will be reducing and there will be some permanent deformation that will be there inside the concrete. Okay, so this is when I am loading till the peak load. Okay, now what will happen at the post peak, like after peak, what will happen? So what will happen, the micro cracks that they have formed, they will combine to form a larger crack, which will cause the softening of concrete. So all the micro cracks that have formed inside the concrete, they will combine and form a larger crack, and concrete will lose its load carrying capacity and it will show a brittle failure. Okay, and now if the load is removed, there will be a large permanent deformation that will remain, with unloading curve much flatter, indicating there is a stiffness loss. Okay, so this is why concrete shows a non-linear inelastic behavior. It is because of the micro cracking, the bulging of cracks, the growing of cracks that happens at different stages of loading. Now, since the behavior is non-linear, there can be multiple ways in which a modulus of elasticity value can be of a concrete can be estimated. Why? Because of non-linearity, the ratio of stress versus strain that represents MoE will change with the slope of the line. So we know, like this is the, suppose this is my stress versus strain curve, so the slope of this line represents the MoE value. Now since my stress versus strain profile for concrete is non-linear, the slope is not constant, so they won't be like one particular MoE value that we can define. There are different types of MoE. Okay, so what are these different types? So first is the initial tangent modulus, where slope of stress versus strain at the initial loading point is taken as the MOE value. So you can see here in the curve, at this point, whatever slope is there of stress versus strain curve, that is known as initial tangent modulus. Okay, then second is the instantaneous tangent modulus. Okay, where MOE value is estimated at any point by drawing the tangent at that point. So suppose this is my stress versus strain profile. So at any point, if I will draw a tangent, it will give me the slope of line at that point, and that is known as instantaneous tangent modulus. Third is the secant modulus, where the first point and the last point, that is still ultimate load, is used to determine the MOE value by calculating the slope of line joining 2 points. So in secant modulus, what I will take, one point will be this. So this will be suppose my x1, y1. Okay, and the second point will be up till my elastic limit. Okay, so suppose this is my elastic limit. Okay, till pu. Okay, this till here. Okay, so this is my x2, y2. Okay, so the line joining these 2 points I will use to determine the modulus of elasticity, and that is known as secant modulus. Okay, and the last one is known as chord modulus, which is similar to secant modulus, but here the 2 points can be anywhere between the 0 point and the pu value. Okay, so in between those, if I will take 2 points, then the slope of line joining those 2 points will represent the chord modulus. Okay, so generally modulus of elasticity we determine up till the point where the concrete is showing some elastic behavior. Okay, so up till that point we can determine the modulus of elasticity. That will be my last point for the secant modulus. So So these are the like four types of modulus of elasticity. Now, how we determine modulus of elasticity of a concrete sample? There are two methods. One is known as static MOE and one is known as dynamic MOE. So first we'll talk about static MOE. So in this, MOE is determined using uniaxial tension or compression loading. Okay. So in static MOE, there are several cycles of loading and unloading that is performed on the concrete, with the load varying between zero to peak load, like not from zero to peak, but in some range between zero and peak. Okay. So multiple cycles of loading, it ensures that creep and hysteresis effect are getting nullified, and the MOE value that I am determining it is accurate. And since we are operating on some level between peak and zero, so the MOE here that we obtain is known as chord modulus. So as we discussed here, in chord modulus we take two intermediate points. So in this, since we are operating between zero and peak, so whatever value of MOE that we are obtaining, it is known as the chord modulus. Okay, so how we perform this test? Okay, so for conducting static MOE, one can follow ASTM C469 guideline, which says that the load is applied in multiple cycle between PU by 3 to PU by 9 range. So suppose we know the ultimate load. Okay, so in the range of PU by 9 to PU by 3, we apply the loading cycles on concrete, and the loading rate remains constant at 140 kilonewton per centimeter square per minute. Okay, so if we can see the image here, so this image is like taken from actual testing setup of one of my sample being tested for MOE in concrete lab in IIT Bombay. So in the first image you can see this is an extensiometer. So this is known as an extensiometer. Okay, so which is fixed on the concrete surface to record the strain in concrete when the load is applied on the concrete. Okay, or we can say some stress is applied on the concrete. And in the second image, it shows the table of a software where we define the cyclic loading. So initially there is a preload that is highlighted in this green. Okay, just a small amount to stabilize the concrete under loading, and then there are multiple cycles of loading and unloading between pu by 3 and pu by 9 load. So you can see here, this will be pu by 9, then pu by 3 one cycle, pu by 9, pu by 3 2 cycle, pu by 9, pu by 3 3 third cycle, pu by 9, pu by 3 fourth cycle, and then it is final unloading. So here I have used 4 cycles of loading and unloading, and for all the cases my loading rate has been constant, and the time for which I am retaining a particular load is constant. Okay, so this is how we define the function for static modulus of elasticity. And behind this image you can see that there is a cylinder, okay, where you can see how this extensiometer is also attached. Okay, it is just blurred, but you can have a sense how this extensiometer is attached on the concrete sample. Now, here in the first image, the top image shows the loading profile of what we saw in the figure, like in the table previously. So you can see this is my preload, then this is PU by 9, then I'm going to PU by 3 retaining for some time, then PU by 9, PU by 3 again, PU by 9 again, PU by 3 again, PU by 9, PU by 3, and then PU by 9 I am coming here. Okay, and the bottom image shows the stress versus strain profile that is recorded. So here there are three colors if you can see. There is green color, there is pink color, and there is a red color line. So green and pink are the two extensiometers that I have fixed on the opposite phases of the cylinder. So suppose this is my cylinder. So one extensiometer I will fix here and one extensiometer I will fix here. So these green and pink represents the data that has been collected by the two extensiometer, and red represents the average strain value of from the two. Okay, so if my concrete surface is flat and the stress is uniformly applied, then the strain will be uniform throughout the sample. So to verify this, so this two extensiometer should not show much deviation if the strain is happening uniformly across the sample. To verify this, we also record the standard deviation between the two extensiometer data, which you can see in the second figure. Okay, so standard deviation is very small in this case. You can see this is my mean, and across mean, my deviation from mean is very small. So standard deviation is within 5% here. Thus, this testing will give me a reliable result. So if my surface is not plane, or if the loading is not axial, or if the extensiometer are not fixed attached properly, the standard deviation will be very high. And the code says that it should not be more than 20% from mean. So if it is more than that, then the testing should be stopped. The error due to which the reason due to which the error is coming should be checked upon, and the test should be repeated. Okay, so this is how we determine the static modulus of elasticity. Now, the MoE value corresponding to actual loading of concrete is known as dynamic modulus of elasticity. So instead of using static loading, we apply a longitudinal vibration on the concrete sample, typically in a frequency ranging from 100 to 10,000 hertz, and this allows us to obtain a fundamental resonance frequency which occurs when the sample specimen length L is equal to the half of the wavelength of the vibration. Okay, so when L is equal to half of the wavelength of the vibration, then the frequency at which this is occurring is known as fundamental resonance frequency. And for this, we calculate the dynamic modulus of elasticity using this formula. Okay, so here n is the resonant frequency, L is the length of my sample, and rho is the density of my sample. So this method is standardized under ASTM CE 215 guideline, which specify the procedure of measuring the resonance frequency of a hardened concrete. And one commonly used approach for measuring this resonance frequency is the impulse excitation testing. Okay, like you can see in this figure. So in this impulse excitation testing, what is done? We lightly strike the concrete sample and measure the vibration response using sensors. Okay. So this you can see in the image. Okay, using this rod, we are striking the concrete sample, and then using the sensors. Okay, we are recording. Okay, so here are the sensors. So using this, I am recording the vibration inside the concrete. So and using this test, we can also evaluate the change in MoE value with increasing concrete age, like you can see in this second figure. Okay, so at different age, we can see how the MoE value is changing over time. Okay, so by using dynamic modulus velocity, we are evaluating the concrete's elastic property more accurately under real world vibration condition, making it more useful for like examining some bridges, pavements, or high performance concrete in application world. Okay, so this is known as dynamic modulus of elasticity, but generally in lab we perform static modulus of elasticity. Now, there can be different types of MOE value based on the direction and the type of deformation. Okay, there is longitudinal modulus, which is also known as axial or Young's modulus. Okay, so the ratio of axial stress to axial strain when a material is subjected to uniaxial loading is known as longitudinal modulus. Okay, then there is transverse modulus, which is known as shear modulus or rigidity modulus G, and this is the ratio of shear stress to shear strain when the material is subjected to shear loading. So, based on the loading and the direction of deformation, you can see these two are different. Both are representing modulus of elasticity, but they are in the different direction. Okay, so this is E represents longitudinal modulus, which is given by stress upon strain, and G is also representing stress upon strain, but this is shear stress upon shear strain. Okay, and then there is volumetric modulus or known as bulk modulus, which is designated by K, and it is the ratio of hydrostatic stress to volumetric strain when the material is subjected to uniform pressure from all direction. Okay, and it is represented by this equation: volumetric stress upon volumetric strain in the material. Okay, so depending on the direction of loading and the type of deformation, my modulus of elasticity can also vary. So how these MOE values are related? They are related by Poisson's ratio. Okay, so you can see here the relationship between E and G. So G is equal to E upon 1 2 into 1 plus nu. Okay, and this nu is the Poisson's ratio. Okay, and what is this Poisson's ratio? It is the ratio of lateral strain to the longitudinal strain when the material is subjected to uniaxial loading. So suppose this is my concrete. Okay, so this is in this direction I have longitudinal strain, and in this direction I have lateral strain. So the ratio of elongation or the strain in this direction to the strain in this direction, it is known as Poisson's ratio. Okay, and it represents how a material deforms perpendicularly to applied stress when stretched or compressed. Okay, so lateral upon axial. So okay, so this is longitudinal or we can say axial, and this is lateral. Okay, and this negative sign ensures that the Poisson's ratio is positive since material typically contracts laterally when stretched or expand. Okay, when it is compressed axially, when stretched or expands, when it is stretched or expands laterally when compressed. Okay, and for concrete, it lies the this value of Poisson's ratio lies in the range of 0.15 to 0.25. Okay, so in this figure, you can see all three types of strain under axial loading of concrete cylinder. So this represents my longitudinal strain that we generally measure using static modulus of elasticity. This represents my lateral strain, okay, which is decreasing as the load is increasing, because like this is under compression. It like if this value is positive, decrease is positive, then this axial value will become positive. Okay, if this is positive, then this will be negative, so that's why the opposite sign. And this represent the volumetric strain, okay, of the material as the stress is increasing. Okay, and this bulk modulus is also related to the elastic modulus using this equation. Okay, so we can relate all different types of modulus of elasticity if we know the Poisson's ratio and one of the MOE value among the three, in between the three. Now, how concrete can affect the modulus of elasticity? So first is the strength. So MOE is directly proportional to the compressive strength of concrete. It means that stronger is the concrete, more stiff, more it is more stiffer, and it shows a higher MOE value. And in general, MOE is equal to 5000 under root FCK. If we follow IS 456, so by this formula we can have an estimate of what is the MOE value and how it is related to the compressive strength. Now, in the figure, one can see aggregates are stiffer and have a higher MOE value, and while paste is comparatively paste has comparatively lower MOE value and concrete lies in between. So the proportion of my aggregate and the cement paste will also affect the MOE value. Okay, so second is the cement paste. Now, as the porosity decreases, the MOE value of cement paste increases, so MOE value of concrete will increase. So you can imagine here, if my MOE value of cement paste will increase, then eventually my MOE value of concrete will also increase. Aggregates, larger proportion and lower size fraction of aggregates results in a higher MOE value of concrete. So we have seen already aggregates have a higher MOE value than concrete. So if I will increase the proportion of aggregate, then in total the MOE value of concrete will also increase. Concrete moisture conditions. So wet concrete shows a higher MOE than dry concrete by a factor of around 0.15. Okay, so this is all observed that wet concrete shows a higher MOE value. And finally the age of concrete. So with age, MOE value of concrete will increase due to densification of pore, and like due to decrease in porosity and densification of my concrete matrix. Okay, so this is like very common, we already know why this is happening now. Okay, so this is how different concrete factor can affect the MOE value. Now, based on the discussion on MOE, just try to answer these three questions. And in the meantime, if anyone has any doubt related to MOE, they can ask. Are there any doubts? Okay, no. Just try to answer the first question. A concrete mixed with high aggregate stiffness and low water to cement ratio is expected to have. Okay. Can anyone else try to answer? Any other answer from anyone? Okay, so the correct answer for the first question will be A. Why? Let's see. Okay, so since I have higher aggregate stiffness, it means that aggregates is since I know aggregate contributes heavily to the MOE of concrete, so high aggregate stiffness will contribute more to the total overall stiffness of concrete. Why? So it will increase the MOE of my concrete. And lower the WYC ratio, since lower W, if there is low WYC ratio, then there will be low porosity in my concrete, and this will make my paste stronger, and it will increase my MOE value. So both of these will increase my MOE of concrete. While since there is low WYC ratio, it will also reduce the long-term deformation in concrete due to creep. So how it is reducing the deformation due to creep, we'll see shortly when we'll discuss about creep. But generally, if there is low water, then there is low chances of creep to occur in my concrete. So the correct answer will be A. Now, question number two. Which of the following statement about volumetric modulus of elasticity of concrete is true? Can anyone answer for what? Can anyone answer question number two? Okay, so let's see the answer. For second question, the correct answer is B. Okay, why? So the volumetric modulus that we are talking about here is also like known as the bulk modulus, and it relates how a material deforms under a uniform pressure, like a hydrostatic stress. Okay, and this pressure includes both compressibility, since it is acting from all the side. So it will include both compressibility, that is the bulk response, and the shear resistance of the material. So that's why it accounts for both bulk and the shear deformation effects. Now, question number three: if the Poisson's ratio of a concrete specimen increases, what is the expected effect on the transverse modulus? So, what will happen if the Poisson's ratio of concrete increases? I would like to expect to like more responses from everyone so that it can be an interactive session. Just try to answer like from whatever you are able to think about the question. Even if it is wrong, just try to answer. So can I see any answer from anyone else? Okay, so for the third question, the correct answer is B. Why? So if you see the relationship between Poisson's ratio and strain, lateral strain. So this is the relation that we saw. Okay. So a higher Poisson's ratio means that under compression, the material expands more laterally. Okay, making it more deformable. And so since lateral deformation is related to transverse stiffness, so we can say that it decreases as lateral strain becomes more pronounced. Okay, so if this will increase, it means that this has increased, and if this has increased, there is more deformation laterally, so transverse modulus is decreasing. Okay, now the next mechanical property that we'll discuss is fatigue. So what does fatigue in concrete mean? So it refers to the progressive weakening and eventual failure of a material when the material is subjected to repeated or cyclic loading, even if the supply stress is much lower than the ultimate strength of concrete. So, simply saying, it's like I am applying a load on concrete and then removing it, and then applying it and then removing it in a cycling manner. Now, here, unlike a single overload failure, damage accumulates over time due to repeated stress application, leading to microcrack growth and eventual failure. Even though the load that I am applying is much less than PU, still the failure can happen due to repetitive loading and unloading, due to which the microcracks are growing and eventually causing failure. Now, how this failure of concrete happens under fatigue loading? So, the failure process is of three stages. During the initial uh, cycle, the microcracks begins to grow near the ITZ of concrete. Then, as cyclic loading continues during the intermediate cycle, these microcracks they link up and grow, showing some visible crack signs. And also, with increasing cycles of loading, the stiffness of concrete decreases, and as the stiffness of concrete decreases, the deformation per loading cycle will increase. Okay, and finally, As the crack reaches a critical size, so these micro cracks which are linking up and growing, as they reach the critical size, there is a failure which is generally brittle in nature and causes collapse of concrete. Okay, so this is how fatigue grows in concrete under repetitive loading. Now, fatigue can be of two types, either when the loading is continuously applied but at a very slow rate, or when it is cyclic in nature. So, the first one is known as creep fatigue, where the loading is continuously applied but at a low rate. And the second one, where the loading is applied in cyclic manner, it is known as cyclic loading fatigue. So in this slide, you can see in the first figure how with increasing duration of fatigue loading from rapid loading to 50 days loading. So this is like rapid loading and this is like 50 days loading, the stress versus strain response is varying. So in rapid loading, suppose P kilonewton of load was supposed to be applied, it is applied in a rapid loading rate. However, while in 50 days loading, the same P kilonewton load will be applied with a decreased loading rate or in a increased time duration. So as fatigue in concrete increases, the concrete shows more deformation and hence the MoE value decreases. So you can see at a certain applied stress value, there is more deformation when the loading is applied slowly and for a longer time. Okay, so this is due to fatigue. In the second figure, we can see the cyclic loading fatigue. So with cycles varying from 1 to up till 3.4 lakhs, you can see how the variation in stress strain profile is happening for concrete. So we can see with increasing cycles of loading, the deformation in concrete starts to increase at the same stress level, which is due to high fatigue cracking. So this like after 3.4 lakhs of loading cycles, you can see the concrete is deforming more with increasing stress as compared to the first cycle loading. So that this was due to fatigue. Now, after fatigue, there is bond strength of concrete. So, bond strength refers to the adhesion and the mechanical interlock between the concrete and the reinforcement steel. So, we have already talked like in site when we go, the concrete that we are using, it is reinforced concrete. Why? Because concrete is weak in tension. So, to enhance the tensile strength of concrete, we use the reinforced concrete. So, in the reinforced concrete, we have a concrete and we have a reinforcement that is embedded inside the concrete. Okay, and the bond strength between this concrete and the reinforcement is also an important parameter in load for load transfer, crack control, and structural integrity. Okay, now there are three primary mechanisms that govern the bond strength of concrete and reinforcement. First is the adhesion. So adhesion refers to the bond between the cement paste and the surface of the reinforcement. Okay, then there is friction, which results from the resistance that is developed due to the roughness of the rebar and the hardened concrete, particularly when the concrete contracts due to shrinkage. Okay, so this is my reinforcement and this is my concrete cover. Okay, so if my reinforcement surface is rough, it will have a frictional effect with the concrete, particularly when it is in uh, shrinkage condition. So if there will be some frictional effect, it will increase the bond strength at the interface, and that's why the second mechanism is friction. And the third mechanism is the mechanical interlock which can happen between the ribs on the reinforcement and the surrounding concrete. So these reinforcement that we embed in the concrete, these are not plain reinforcement that, but they are like ribbed or deformed surface reinforcement. So these ribs ensures that there is a proper bonding with concrete. Okay, to enhance the bonding of reinforcement with concrete, we have ribs, and these ribs cause mechanical interlock with the concrete, which enhances the bond strength. Okay, so all these combined together contributes to the bond strength of the reinforcement in concrete. Now there are three main factors that affects the bond strength. Okay, first is the compressive strength. So as compressive strength will increase, the adhesion of concrete with the reinforcement will increase. Why? Because the paste content will increase and thus the bond strength will increase due to better adhesion. Second is the reinforcement type and surface texture. So suppose I am using a coated reinforcement. So that coating can decrease the bond strength if it will decrease the frictional resistance of the reinforcement with concrete. Okay. And in case of uncoated reinforcement, if I'm using a unribbed reinforcement, it will show lower bond strength than a ribbed reinforcement because there is no mechanical interlock with the concrete. Then at last, reinforcement diameter and development length. So both of these are like entities. If both of them will increase, like if I will increase the diameter or the development length is the embedded length. Okay, so as they will increase, the adhesion and the frictional effect of the reinforcement with concrete will increase, and thus the bond strength will increase. So higher compressive strength will increase the bond strength, coated reinforcement will decrease the bond strength, and a ribbed reinforcement will increase the bond strength. And reinforcement diameter and development length, as they will increase, it will increase the bond strength of concrete. So here one can see how bond strength of concrete is determined. So this again is from one of my setups in concrete lab here in IIT. So in the first figure, you can see a universal testing machine where a pull-out frame is attached. Okay, so this is the universal testing machine, and this is the pull-out frame. Okay, so now here you can see a reinforced concrete sample, and from the bottom of this plate there is a hole to using which my reinforcement is gripped to this grip at the bottom, and while this frame is gripped at the top. Okay, so when I will apply some pulling force, so what will happen? My reinforcement will be forced to pull out from the concrete while my frame will be fixed. So my concrete will be fixed. Okay, so now when I'm applying load to record how my reinforcement is slipping from inside concrete, I have attached a extensometer at the top of the concrete. So at the top there will be like small portion of reinforcement coming out. Okay, and at the top of this the extensometer is attached. Okay, so in the second image, you can see how reinforced concrete fails on pull-out testing. Okay, so in this direction, the pull-out force was getting applied. So while when it fails, it shows some cracking pattern like this. And then in the third figure, you can see how bond stress is varying with the slip that I have recorded using this LVDT. Okay. So as the loading increases, the bond stress increases. Then after a peak, as the stress exceeds the strength of the bond failure occurs, and there is a large slippage in the reinforcement after the failure of bond, as you can see. So compared to 7 days, 28 days curing, as the strength of concrete increases, you can see the bond strength also increases. Now try to answer these questions again. So first is like related to the fatigue, and then we'll see some question related to the bond strength. So question number 4 says, which of the following condition will increase the fatigue life of concrete the most? And in the meantime, if anyone has any doubt regarding fatigue and bond strength, they can ask. Okay. What will be the answer for question number 4? Okay, so for question number 4, the correct answer is B. Why? Because well graded aggregate, they improve the concrete's density, and they will reduce the micro cracking under cyclic loading. Okay, so With well graded aggregate, I will have a reduced porosity that will minimize the stress concentration, and it will cause a better fatigue resistance in concrete. Okay. Question number 5. When comparing fatigue failure in normal strength concrete and high strength concrete, which of the following is correct? Okay, so five for five, both A and B can be correct. Okay, how? So in normal strength concrete, it has more micro voids and a weaker ITZ. Okay, so since the ITZ is weaker, it is more susceptible to fatigue failure. Okay, so that's why normal strength concrete has a shorter fatigue life due to weaker ITZ and higher porosity. However, in high strength concrete, being denser and less porous, it generally shows a better fatigue resistance due to its increased toughness and lower porosity. Now, question number 6. What is the primary mechanism responsible for fatigue failure in high strength concrete? Okay, so for question number 6, the correct answer is B. How? So in high strength concrete, what happens? My IT set, it still is the weakest link. So in repeated cyclic loading, this IT set gradually weakens. Uh, the loading gradually weakens due to this IT, due to this repetitive loading, the ITZ will gradually weaken, and it will cause the fatigue failure. Okay, and A can also be correct, like brittle fracture. So generally, when we talk about high strength concrete, we observe brittle fracture of material. But the primary mechanism responsible for that is the progressive ITZ deterioration. Now, question number 7. This is related to bond strength. So in pull-out test, a smooth rebar embedded in high strength concrete fails primarily due to. So I have a smooth rebar embedded in a high strength concrete. Okay, so for 7, the correct answer will be A. Why? So, for smooth rebars, the bond strength relies heavily on the adhesion with the cement paste and the steel surface, because there is no friction effect right now, and there is no mechanical interlock, because since the rebar is smooth, so it highly relies on the adhesion between the cement paste and the steel surface. Now in high strength concrete, it has a dense matrix, so the bond is primarily with adhesion base. So under loading for smooth rebar, this adhesion is the first to fail. Okay, so that's why the failure, adhesion failure at the cement phase interface is the primarily responsible for in pull out testing. So that mechanical interlock failure and all, it mainly occurs in deformed rebar and not the smooth one. So that's why here the adhesion failure is the reason. Now question number 8, bond strength between reinforcement and concrete decreases significantly when. Okay, so the correct answer will be B in this case. How? So epoxy coating is like a smooth coating that is done on the reinforcement. So generally these coatings, they are done to protect the reinforcement for from corrosion effect, since they are like an insulator coating which will cut down the interaction between the reinforcement and the environment. So that corrosion part we'll see later on in like week 11 maybe. Okay, so epoxy coating, it is a smooth coating on the reinforcement, and it reduces the adhesion between the reinforcement and the concrete. Okay, so it can cause significant reduction in bond strength. Okay. Okay, so this was all about fatigue and pull out bond strength. Now the next part of our discussion is in hardened concrete properties, creep in concrete. So what does creep mean? So simply saying, creep is a gradual long-term deformation of hardened concrete under sustained loading, which causing an increase in strain without a change in applied stress. So it is a gradual long-term deformation. Now this load may not be even around failure load level, but since it is sustained load acting for a long time, it results in deformation. Okay, so as it is written in the second point, it occurs as a slow continuous movement within the material leading to progressive change in shape over time. Okay, so slow continuous movement. Okay, so load is not near the failure load, but still due to the slow continuous movement, these changes that are occurring within the material and which leads to failure at the end. And what is the end result? So this creep phenomena affects the structural stability by affecting the dimension and the internal stress distribution. Okay, an example of creep action we can see in the image here also, where we have a bridge deck under continuous loading. So in this loading, the deck shows a vertical deflection, or we can say creep deflection, as you can see here. Okay, so here there is a creep deflection that has occurred due to continuous loading, where the beam has deformed over time. Okay, so you can see here in the image, like this is load, this is beam. So under continuous loaded, the beam will appear like this. It will deform over time. Okay, so this is due to creep. Now the same thing we can understand from the stress strain relationship as shown here also. So under a constant applied stress epsilon naught, as you can see here, at time t naught, a constant stress was applied epsilon naught, uh, due to the modulus of elasticity of concrete, there is a continuous increase in the strain as the stress is sustained after a time t under loading. Okay, so initially there is some elastic strain due to modulus of elasticity, then there is a continuously increasing strain in concrete under sustained loading. Okay, and after time t, you can see what is the effect of creep, that is the increase in strain value. From like this creep is total strain minus initial elastic strain will define the creep strain. Now, what happens if I will remove the load? So this process is known as relaxation or creep recovery. And so when the continuous load is removed, the strain decreases immediately. and the amount of decreased strain is equal to the elastic strain at a given age. So at a given age, what is the elastic strain in my concrete, that much strain only will be recovered. Okay, and this quick recovery is then followed by a continuous decrease in strain, which is known as creep recovery. That is a part of total strain suffered by the concrete. So here you can see in the image, initial at sustained loading, the creep was increasing, it reaches the particular value, and then once the load is removed, there is a elastic recovery, and then there is a creep recovery part. Okay, now this is like the ultimate recovery, and this is the irreversible part of creep. Okay, so there's still some irreversible strain left after creep. This is due to the deformation that has occurred in the concrete under the sustained loading period. So in the sustained loading period, there will be some cracking that has occurred in concrete. There will be some deformation that has occurred in concrete, and that will lead to contribute in the irreversible creep part. Now we have seen what is creep, but how creep occurs in concrete. So the first hypothesis to explain this concrete creep was given by a scientist named Freycinet. Okay, after his famous observation of the deformation of a bridge located in France. Okay, in 1926 to 1929. So this way, he was the first person to give the hypothesis of to explain concrete creep. Okay, so for this author, the creep would be a shrinkage amplified by applied stress. Okay, so it was like nothing but shrinkage is happening in concrete, which is amplified by stress, and thus this theory implies that the loss of water through drying is greater in loaded concrete than in free concrete. So shrinkage is loss of water, and it under loaded concrete it will be more than in free concrete. So that he related to creep. Now, another scientist named Lyman in 1934, he suggests three possible fundamental causes of creep. That is crystalline sliding, movement of absorbed water in the cement hydration product, and the viscous flow. Okay, and all these causes that he proposed to this date can be included, like all the causes of creep that are proposed to the to date can be included in these three broad categories. So whatever we understand about creep, like whatever different theories that they are that are present about creep, they can be summarized in these 3 points that was first proposed by this Lyman author in 1934. So if anyone wants to read like dig deep more into the theories of these two researchers that I have mentioned the references of their article also, that you can search and have a look. Okay, now if we try to understand what Lyman was trying to say in his three possible causes, so in a time dependent deformation of concrete under sustained loading, multiple activities are taking place. There is a viscous flow of water in gel pores, which is the reversible part of creep. So, what happens? Concrete contains CSH gel with gel water inside fine capillary pores. Okay, now under sustained loading, what happens? The water is gradually forced out from the gel pore. So inside the gel pore, the water which was there, it will gradually force out out of the gel pore and the sustained loading, which will lead to slow deformation over time. Okay, and this is the reversible component of creep, meaning that some of the deformation can be recovered if the load is removed. Okay, so this is due to the movement of gel water under loading. Then there is micro cracking and stress distribution, that is the irreversible part of creep. Okay, so under sustained loading, it causes gradual formation and growth of micrografts that we have already understood near, especially near the ITZ. So these cracks, they will propagate over time and they will cause some permanent deformation in concrete. And it also increases the compliance, that is the strain per unit stress. Okay, so amount of strain that is occurring per unit stress, or we can define the stiffness of concrete, it decreases the thickness and increases the compliance of concrete, and this is the irreversible part of creep. Why? Because crack has occurred and deformation is now permanent. And the third thing that happens in the sustained loading is sliding and rearrangement of CSH sheets. Okay, so under prolonged loading, what happens? The weak van der Waals forces between the CSH layer, they allow slow sliding and rearrangement of the sheets. And due to this, there is deformation in my concrete, which is a long term deformation and a irreversible part of creep. So there is water movement, there is crystalline sliding, and there is cracking in concrete, which occurs under sustained loading. Now, how my concrete uh, property can affect creep? So first of all, we will have first we'll see from material point of view, like in which we first is the aggregate proportion. So it is known that aggregate undergoes very little creep. It is really the cement paste which is responsible for the creep. Okay, so instead of like undergoing creep, aggregates retards the creep in concrete through restraining effect on the creep magnitude. The paste is the one which is creeping under load, and the creep in the paste is restrained by the aggregates. Okay, so stronger is the aggregate, more is the restraining effect, and less will be the magnitude of the creep. So, like higher MoE value of aggregate will result in less creep, and lightweight aggregate will show substantially higher creep than normal weight aggregate. Okay, so my aggregates, what they happen, they restrict the crack growth. Okay, and it is the cement paste which is creeping over time. So, aggregate have a positive influence or on increasing the creep value. Okay, and it is observed that from experimental result, it is observed that an increase in aggregate proportion from 65 to 75% of volumetric content can decrease the creep by 10%. So this is how much aggregate can contribute to the creep. Now, after aggregate comes the influence of the paste proportion. So, as said earlier, the paste is the part in concrete which is creeping. So, the amount of paste content and its quality is the one of the most important factor influencing the creeps, because since it is the paste only which is creeping. So, a poorer paste structure will undergo higher creep. So, we can say creep increases with increase in W by C ratio. Okay. And last here is the age of concrete. So as concrete ages, the hydration proceeds, and thus the quality of cement paste improves over time. So my creep will be inversely proportional to the strength of concrete. So we can see the same from the figure also, where creep is plotted against age with the application of load. So you can see as the age is increasing, the creep value is decreasing. Now, after mixture proportion factors, the second factor is the dimension, which is represented by the volume to surface area. Okay, just a second. So it is observed that a higher surface area will result in more creep. So from a higher surface area, what I mean, a thin section or a small element. Now what happens in a thin section or small element like slab or beam, they have more exposed surface. So if my volume to surface area is low, it means my surface area is high. So if I have more exposed surface, it will allow moisture to escape more quickly. So greater moisture loss will lead to higher creep deformation over time. Okay, so that's why higher surface area will result in more creep. And conversely, lower surface area will result in less creep. Okay, why? So, in large, massive concretes like dam and thick walls, most of the moisture remains trapped inside concrete, which reduces the creep effect. Okay, because there is a low surface area. The same can be understood from the graph, where one can see the ratio of 30 years creeps to elastic strain. It is decreasing as the volume to surface area ratio is increasing. So, this volume to surface area ratio, it will increase as the surface area will decrease. Also, with the age of concrete, we can see that at the age of concrete at which the load is applied. Okay, so as the age of concrete increases, the ratio of creep also decreases. Okay, so this is the effect of the dimension of my concrete. Finally, it is the effect of external factor, which includes RH and temperature. So relative humidity part is simple. If relative humidity will be low, drying will be fast, so creep will be more. The same can be seen from the curve in figure 1. Okay, so you can see at low relative humidity where there was higher creep after a certain time of loading compared to a high relative humidity. Now, for temperature, it is observed that when the concrete is cured at a certain temperature, suppose for 21 degrees Celsius, and then it is heated to temperature, test temperature 1 week before loading, it exhibits higher creep compared to concrete that is continuously cured at the test temperature. Why? Because in the first case, the higher creep is due to drying of moisture. Okay, plus the thermal cracking that is due to the incompatibility in the paste and the aggregate. Okay, since I have heated the concrete, it has become dry and there is incompatibility in cement paste and aggregate due to heating, which leads to higher shrinkage. While in the second case, when concrete is continuously cured at test temperature, the concrete develops as a more stable microstructure, which reduces the creep deformation under loading. Okay, so here there is a stable microstructure, while here it is a unstable microstructure. That's why it is showing higher creep. Now, based on this understanding of creep, try to answer these following questions. And in the meantime, if you have any doubts related to creep, you can ask. Why epoxy coating is used? Because it will prevent corrosion in reinforcement to happen. Okay, so when you talk about bridges and all, generally in road construction we don't use epoxy coating. We generally use epoxy coated rebars and bridges which are near the seashore, like in Bombay. All the bridges that you see, they are very near to the shoreline, or the environment is highly corrosive. So for those we need some special kind of reinforcement, and that's why epoxy coated rebars are used. That epoxy is an insulation material. It won't allow external ions to react with the reinforcement. How these ions are reacting with the reinforcement we'll see shortly in the coming weeks. Okay, but for now just remember that coating is a barrier which hinders the reaction between the reinforcement and the surrounding, and it lowers the corrosion rate. What about creep? For completely dry concrete there will be very low creep. Okay, it is the moisture, the movement of moisture and the deformation of my crystal sliding that occurs. Mainly it is the movement of moisture. Okay, that causes creep. So this creep and shrinkage, both concept are related to the moisture content in concrete. They are highly dependent upon the moisture content in concrete. Try to answer this question first now. What is the primary reason why high strength concrete exhibits lower creep compared to normal strength concrete? Okay, so for 9, the correct explanation or the primary reason will be the denser microstructure and low porosity. Yes, there is high cement content, but the primary reason is the dense microstructure and the low porosity. So what happens? This dense matrix will reduce the ITZ porosity, and it will cause a stronger paste aggregate matrix bond, which will reduce the creep. Okay, so stronger bond will reduce the creep in concrete. Now, second, which environmental condition accelerates creep in concrete the most? Okay, for 10th, the correct answer will be A. Why? Because high temperature will accelerate the moisture movement that is happening, and low relative humidity will increase the drying in concrete, and both of them will increase the creep strain in concrete. Okay, so the movement of moisture, like we have talked here, right? It is the movement of moisture and the cracking and the sliding. So movement of moisture is also a critical part. So here also you can see, as the temperature is increasing, the creep is increasing, and as the relative humidity is low, there is more creep due to more drying of concrete. Okay, so that's why high temperature and low humidity will accelerate the creep in concrete. Now question number 11. Which factor has the most significant influence on the long term creep in hardened concrete? Can you even tell me the answer for question number 11? Okay, I have received two answer. The correct answer will be A. The most significant influence is caused by the W by C ratio. Why? Because a higher W by C ratio will increase the porosity, and this will lead to higher creep because of increased moisture movement and weak paste structure. Okay, so that's why the most significant influence is caused by the water to cement ratio. Okay, now we'll move ahead. Okay, let's see the next part. Now, the next thing is the prediction and measurement of creep. So, first we look at the prediction part. Okay. So, by prediction, we mean estimation of creep in future, depending on the known or the known present state or the past state. Okay. So, for this, there is a method standardized by American Concrete Institute as ACI 219 model for creep prediction. So it's an empirical method used to estimate creep strain in concrete over time, and this is based on experimental data and considers key influence factors such as time, relative humidity, and mixture proportion. Now, when talking about quantifying creep, there are two terms that are commonly used. One is creep coefficient and one is compliance function. Okay, so the creep coefficient is one of the most common description to express creep behavior in concrete, and it is computed as a ratio of creep strain to the elastic strain. So elastic strain we have seen it is the initial strain that is occurring when load is applied to concrete due to the elasticity models of concrete, and the creep strain is the strain that is growing over time under sustained loading. So the ratio of creep strain to elastic strain is known as the creep coefficient, and compliance function is another expression to describe creep, and it is defined as the strain per unit stress. So the total strain in my material per unit stress that is applied, it defines the compliance function. Now, as per ACI method, the creep coefficient after a time t under loading, knowing that after some time t naught the load was applied, so you can see this creep coefficient t dash t naught. So after time t, what is the creep? Like, this is my curve. Okay, so at time t naught I have applied the loading, and this is the time t after which I want to determine the creep. I want to quantify creep. So this t is this time. After at time t naught I have started the loading, and after how much time t after loading, what is the creep coefficient? So it is given by this expression. So phi t dash t naught is equal to phi u times t minus t naught to the power zero point 0.6 upon 10 plus t minus t naught to the power zero point 0.6. So here phi u is the ultimate creep coefficient and t naught is the age of concrete at loading. So when the at the age of concrete at which the loading was applied. Now, what is this ultimate creep coefficient? It is estimated based on the environmental and material properties. Okay, so phi is given by this formula. Okay, and these are the factors which is defined by different environmental and material property. So this first factor, it is determined based on the age of loading. Okay, second factor is based on relative humidity. Third factor is based on volume to surface area ratio. Fourth factor is based on the slump of concrete. Fifth factor is based on the fine aggregate content, and sixth factor is based on the air void inside concrete. So for each of these factors, different empirical relationships has been derived as shown here. Okay, so depending upon the exposure environment and concrete property, these factors can be quantified and ultimate creep value can be determined. Once we have determined the ultimate creep value, we can determine the predict the strain after a time t, if the loading is applied on concrete at time t naught. Okay, so this is the table for predicting the factor, and this is the final equation. So that was ACI method. Now there is another method for creep prediction proposed by British standard. So here first MoE value is determined using the following equations. You can see here equation. So MoE of concrete at a time t naught is determined if for using this equation. So MoE at 20 days into zero point 0.4 plus zero point 0.6 times strength at T naught upon strength at 28 days. In MOE 28 days, you can determine by this equation. Okay. So once uh, we know the MOE value, we'll move to this figure. Okay. So the strength ratios are like, if you want to know the strength ratio, they are zero point 0.7 for 7 days, 1.17 for 90 days, and 1.25 for 1 year. Once in the MOE values determined, the second step is to use the figure to determine the ultimate creep coefficient, which is based on the MOE, volume to surface area ratio, RH, and the age of application of load. Okay, so suppose my volume to surface area ratio is 150 and my RH is 50% and the concrete age is 28 days. So what how I will determine the creep coefficient? So you need to learn how to read this figure. So you can see here I have volume to surface area ratio. If it is below 100, I need to use the first column. If it is between 100 and 200, I need to use the second column. If it is more than 200, I need to use the third column. Here I have the average relative humidity factor, and here I have the H factor. Okay, so ultimate creep coefficient I can determine for here. Okay, so suppose my MOE value is 150. Volume to surface area ratio is 150. So I am concerned with this column. Okay, now my RH is 50%. So what I will do at 50, I will draw a vertical line. Okay. And my concrete age is 20 days. Okay, at the application of load. So at 20 days, I will find it in interaction, and from that I will draw a horizontal line. Okay, and I will see where this line is interacting this second column. So you can see it is interacting somewhere between zero point 0.2 to zero point 0.4. So I can say my creep value, ultimate creep coefficient will be somewhere around 2.3%. Okay, so this is how I can determine the creep coefficient. So this was about prediction of creep. Okay, we have seen ACI method and we have seen British standard method. Now after prediction comes the measurement of creep. Okay, so here uh, like what measurement we can perform using ASTM C512 method. So this method provides a standardized method for determining creep deformation in hardened concrete when subjected to sustained compressive stress, and it accounts for factors such as moisture loss, age of loading, stress level, and the curing condition. Now, for this for according to this code, my sample should be either a cylinder of 150 cross 300 dimension, or a prism of 100 cross 100 cross 400 Okay. Now, in this method, what is the first step? First step is to determine the MOE value, for which elastic strain is measured by loading the sample up to 40% of its ultimate load and unloading it immediately. So this MOE is like a static MOE that we have seen earlier. Okay, I am loading the sample up till 40%, so zero point 0.4 pu. Up till this value, I am loading the sample and unloading it immediately, and I am determining the MOE value. Okay, and then specimens are loaded to 30 to 40% of its peak value using the creep using a creep frame, and the load is maintained for months or years while keeping the environmental conditions stable, and at different intervals the deformation is recorded. Okay, so I have my sample. Okay, and I have subjected it to a load of 30 to 40% of failure load. Okay, and I have maintained this load and the environmental condition, and with time I am recording how much deformation has occurred in this sample. So that deformation will be how I will determine that deformation. So the total deformation minus the elastic strain. So elastic strain I will know since I know the MOE value. Okay, if I know the MOE value and the stress applied, I can know the elastic strain, so I can determine the creep strain. Since this deformation that I will record, it will be total strain in the concrete. So creep strain I can determine from this value, and then creep coefficient I can estimate. Okay, so sigma phi epsilon cr upon epsilon e will be my creep coefficient. So here in the first image shows the setup arrangement for creep measurement, where you can see cylindrical samples are loaded between a loaded frame at the top and a spring at the bottom, and over time deflexometer using a deflexometer deformation or strain is recorded. Okay, like shown in the second figure, you can see there are different loading frames, and using this deflexometers I am recording the strain in the sample. Okay, so this is how creep is measured in concrete. Now, how this deformation due to creep affects the concrete performance? So we can see in three different domains. So in case of reinforced concrete sample, in RC beam, creep increases the deflection with time, which may be critical consideration in design. So if you will go back to IS 456, you will see a table where creep coefficients are mentioned. Okay, there is a table where creep coefficient are mentioned because this creep effect can be critical in terms of design. Okay, the creep results in gradual transfer of load from concrete to rebar in columns. So when steel yields, further load transfer is to the concrete. So due to creep, there is a load transfer from concrete to rebar, which can cause steel to yield. And once the steel will yield, the load will transfer back to concrete. So this also becomes critical in terms of design of reinforced concrete. And in case of eccentrically loaded RC column, creep increases the deflection. Okay, so suppose this is my column. Now the load is not applied at the center, but somewhere away from the center. So it gives rise to eccentricity. So this is E, this is P. So there will be movement, bending moment that will be created inside the column. And if this load is maintained, then it will increase the deflection and can lead to buckling of my column. Okay. In case of pre-stressed element, there where pre-stressing is applied as a restraining effect, the creep can cause loss of pre-straining of steel, which can result in deformation of my pre-stressed element. And in case of mass concreting structures such as dams, in addition to the differential temperature container inside and outside, creep is harmful for causing cracking in concrete in the interior of dam. Okay, so in case of dams also, creep effect can be harmful. Okay, so mass concreting, it is harmful. For pre-stressed element it can be harmful, and for reinforced concrete also it can be harmful. Now this deformation due to creep, it happens in three stages. So when we talk about deform, like concrete is deforming under creep, there are three stages. Okay, so initial days, first is the primary creep range, where it starts separate, where the creep starts separately and slows down. Then there is a secondary stage where it is progressively increasing at a relatively uniform rate, and then there is a ternary creep range where the strain accelerates the deformation and material finally fades. Okay, now in the second stage where my rate is uniform, I can also have cyclic loading like this. Okay, which results in increasing deformation. Okay, that we'll see in the next slide right now. Okay, so after the instantaneous strain, that is elastic strain, you can see three different stages of creep deformation in concrete. Okay, so here there is a decrease in creep rate, then there is a constant creep rate, and then there is an increase in creep rate. And why this is happening? It is due to the micro cracking in concrete. Okay, so initially my cracks are getting restrained by the aggregate, so that's why the creep is decreasing initially. Then that restraining effect is counterbalanced by the growth of cracking in concrete, so that's why I have a constant creep rate. And finally, my aggregates are not able to restrain the cracks for any further, because crack is growing continuously and they are merging with each other. So I can see there is an increased creep rate as the crack growth will increase. So this is how they are, this is why there are three different stages. Now suppose there are multiple loads that are acting. Okay, so failure due to creep deformation we can predict using Miner's rule. Okay, so this rule is also known as linear damage rule or minor Pelgrin rule. So these two gave the rule. Okay, and it was first proposed by the Pelgrim, by a author named Pelgrim in 1924, and it was further developed by Miner in 1945. So this is just the history from where this rule came. And it calculates fatigue damage based on the number of cycle at each stress. So at a given stress level, the damage fraction can be compared as the ratio of number of cycle at that stress level to the total number of cycle to failure under the stress level. So this is known as SN curve. Okay, so suppose I have a load P acting on a structure. Okay, so after 10 number of cycle it will give me failure. But if I will change the P load quantity, that amount of load, my number of cycles to failure can change. So this curve relates how the number of cycles to failure changes with the secondary creep rate. Okay, so this is known as SN curve. Okay, and now according to minor rules, suppose there are multiple load acting and we know what is the number of cycle till failure that will occur. So amount of load that we have applied and the ultimate load, ultimate number of cycles of that load, summation of that will give me the cumulative damage. And if this D is equal to 1 or if it is more than 1, then I can say that failure has occurred due to that accumulated load or damage due to that accumulated load. Okay, so this is Miner's effect. We'll see one numerical here, like to understand how this concept is applied. Okay, so like just try to solve. These are for numericals, very simple numericals based on this prediction measurement of creep. So just give it a try. Give it a try for question number 12. How we'll calculate the creep coefficient. In the meantime, if anyone has any doubt in this part of discussion, they can ask. Uh, at my screen, there is like some problem that I can't see the message box properly. It is becoming blurred. So the message, the last message that someone sent, I guess it was a doubt that I'm not able to read. If you can type again, it will be good. In the meantime, give it this numerical a try. Okay, I can read now. Sir, if volume changes in concrete due to sustained loading, can say creep. Volume change, it is happening now due to moisture movement. Volume change can happen, and there will be deformation. What is deformation? Okay, that is the change in the volume of the system only, or cracking in the system. So that is also creep. So creep is nothing but deformation that is happening in concrete due to sustained loading. Okay, and volume change can happen like when there will be loss of water, there will be shrinkage, there will be cracking, then volume change is happening, and that is also a creep effect. Okay, can anyone tell me the answer for question number 12? Okay, very simple question. So I know there is a concrete cylinder tested as per ASTM C512 under a sustained stress of 10 MPa. I know the elastic strain at loading and I have measured the creep strain after 1 year. Okay, so what will be the total strain and what will be the creep coefficient? Any answers? Okay, so this will be very simple. Total strain is nothing but elastic strain, that is 0.005, 0.0005 plus creep strain. So that is 0.0021. So this will sum up to 0.0017. So that is total strain after 1 year. And creep coefficient will be nothing but creep strain upon elastic strain. So 0.0012 divided by 0.0005. So it will be, this will come out to be 2.4. Okay, so this is just the simple application of formula that we have heard, that we have seen. Now, question number 13. A concrete member is loaded for 20 days with a sustained stress of 5 MPa. Using ACI 219 model, estimate the creep coefficient at 180 days. Given the ultimate creep coefficient is given to us. Okay, so just try to apply that formula of T minus T naught that we discussed earlier. Okay, I will just show you that formula again if someone doesn't remember. Okay, so this formula we have seen in ACI method. Okay, how we will apply this formula to calculate the creep coefficient? Okay, so simply applying the formula, phi u is given to me. So the answer will be 2.35 times T minus T naught. So T is 180 at the age at which I am determining the creep, and T naught is the age at which loading starts. So that is 28 days to the power zero point 0.6 upon, let me just write this properly, upon 10 plus again 180 minus 28 to the power zero point 0.6. Okay, so this will give me answer of 1.567. So this is my creep coefficient. Okay, I know the age at which sample was loaded. So this is T naught and this is T, the age at which I want to determine the creep. And I have given the ultimate creep coefficient is already given to me. Okay, now I know the ultimate creep coefficient. Okay, how I can determine the total strain if the elastic strain is 0.0008? So can anyone tell me the answer for this part? What is the total strain in the concrete, knowing the creep coefficient and the elastic strain? Can anyone tell me the answer if anyone has calculated? Okay, let me tell you the answer so that we can move fast ahead. So I know the creep coefficient and I know the elastic strain. So I can calculate the creep strain. It is nothing but the creep coefficient times the elastic strain. So 1.567 times the point triple zero eight. So this will give me creep strain. Okay, so this will give me creep strain that will come out to be 0.00216, and then total strain will be nothing but creep strain plus elastic strain. So 0.00216 plus point triple zero eight. So this will be my total strain. So that will be point double zero. Okay, this you can calculate. Okay, it will come out to be. Let me do the calculation. 0.00206. Okay, so this will be my total strain in the system. So knowing the creep strain, you can calculate the total strain if you know the elastic strain. Now, question number 15. In a concrete beam is subjected to cyclic loading with stress ranges. So 50% fracture stress of 5,000 cycles, which has a capacity of 10,000 cycles for failure, it is subjected to, and 40% failure stress of 20,000 cycle, which has a capacity of 50,000 cycles. Now, using Miner's rule, determine whether failure will occur or not. Okay, so you have two stress cycles. Okay, and you know the capacity at which failure will occur. So how you will apply Miner's rule to calculate whether failure will occur or not? Try, give it a try. 0.47. For which question you are saying this answer? 0.00200. Okay, that is correct. 0.47, I don't think so. There is any answer as 0.47. You might have done some mistake in that calculation. Okay. So I will tell you this answer because I don't think so you will find it easy to calculate right now. Now, what minor rule says, like how many cycles we have applied for a certain loading, okay, number of cycles at stress level to the total number of cycles of failure. Okay, so for first loading I have applied 5,000 cycles, and for failure I required 10,000 cycles. So this is my first ratio, and second ratio is I have applied 20,000 cycles of second stress, and its failure capacity was 50,000 cycle. Okay, so this is by n1 by n1 plus small n by capital N for first loading, and small n by capital N for the second loading. So if I will add these two, cumulative of these two cycles, if I will get, it will be zero point 0.5 plus zero point 0.4, okay, which is equal to zero point 0.9. Now, since this cumulative is less than 1, we can say that according to Miner's rules, the accumulated damage in the concrete will not lead to any failure because the ratio is less than 1. Okay. So for failure, I need a ratio of equal to or greater than 1. But right now, my value is zero point 0.9, which is less than 1. So there will be no failure according using Miner's rule. Okay, so this is how Miner's rule is applied. Okay, I hope this part is clear. If not, you can just revisit that discussion again of prediction and measurement, and then again try to solve this question so it will become easier for you. Okay, so we'll move ahead. So like in 15 minutes I will try to conclude the session now. So after creep, the final part in the hardened property is the shrinkage in concrete. So what does we mean by shrinkage? So shrinkage in concrete can be defined as the volume change observed in concrete due to loss of moisture at different stages due to different reasons. Okay. Now, in broad division, there are four types of shrinkages in concrete. There is plastic shrinkage, drying shrinkage, autogenous shrinkage, and carbonation shrinkage. So, plastic shrinkage is the contraction in volume due to water movement during concrete, which is still in plastic state. So, when my concrete is still in plastic state, the contraction in volume due to water movement is known as plastic shrinkage, and it mainly occurs due to loss of water by evaporation from the concrete surface, or it can occur due to water absorption by aggregate if it is not considered while mixture proportion. Okay, so these two can be the reason for plastic shrinkage. So when my concrete is in fresh state, if there is loss of moisture or loss of free water from concrete, then it will lead to plastic shrinkage in concrete. Okay. Now, second is drying shrinkage. It is caused by the loss of surface absorbed water held in gel pores from the CSH gel, and it takes place once the concrete is set. Okay, so plastic shrinkage was in fresh concrete and drying shrinkage in is hardened concrete. This is due to loss of water in fresh state, and this is due to loss of water from hardened state. And in hardened state, the loss of water will occur, the the gel water, if the gel water loses, then there will be drying shrinkage. Okay, now part of the shrinkage can be recovered if I will immerse the concrete back in the water for some specified time, and that is known as moisture movement. Okay, so my gel pores will lose water, and that will cause drying shrinkage, but a part of that I can uh, uh, recover if I will immerse the concrete in water. Okay. Now there is one more type of shrinkage which is known as autogeneous shrinkage, which is a basic shrinkage. Is due to chemical reaction between cement and water. So you have already seen when cement reacts with water, it forms hydrated paste which occupy lower volume compared to this individual entities. So this change in volume due to chemical reaction, it is known as autogeneous shrinkage, or sometimes known as chemical shrinkage. Okay, now it does not include any direct environmental effects such as temperature or moisture change. Okay, it is the natural process that will occur due to hydration, and its magnitude is usually ignored in concrete with W by C ratio more than 0.4. The magnitude is also very small compared to plastic and drying shrinkage. And finally, we have carbonation shrinkage. So when CO2 from atmosphere, it reacts with calcium hydroxide, it forms CaCO3, and this also uses some water and releases some water. Now this conversion of CaOH whole twice to CaCO3, it results in decrease in volume. So this decrease in volume again can bring shrinkage. So that's why it is known as carbonation shrinkage, because due to carbonation there is a change in product which is happening and which is causing shrinkage. Now again, this magnitude of carbonation shrinkage is very small when compared to long-term drying shrinkage. So mainly the drying shrinkage and the plastic shrinkage are the ones which dominate the shrinkage in concrete. Now in this slide I have tried to summarize like broad area of different how shrinkage occur in concrete. Okay, and how it is an issue. So, the primary driving force behind shrinkage is the capillary action and the surface tension that we can understand. Okay, how? So, concrete contains network of capillary pores. So, we have seen there are capillary pores, there are gel pores. Okay, so there is a network of capillary fold filled with water after mixing in concrete. Now, as concrete will lose water due to evaporation or hydration, what will happen? These pores will become partially empty, because from these pores contain the free water that is there in concrete, which is consumed during hydration or which is lost due to evaporation. So if this free water is lost from the pores, they will become partially empty. Now the remaining water forms a meniscus. So like this, the remaining water, it will form a meniscus due to the surface tension effect, okay, on the water surface. Okay, and it will create a negative capillary pressure. So if you see here, this meniscus that will form, it will create a negative capillary pressure or an inward pulling force on the solid matrix, and which can cause the volume reduction or shrinkage. So this is the meniscus, and this is the negative capillary force that is acting on the surface, and this surface has nothing but the cement paste, cement grain or a hydrated product. Okay, so on this it is causing some inward force which can result in shrinkage. Okay, now the water molecule adhere to the cement particle surface to surface tension. So we have seen here, due to surface tension, I am seeing the formation of meniscus. As the moisture evaporates, the curvature of meniscus generates the tensile force. So you can see this tensile force, it is generated on the cement paste, and this stress causes stress on concrete inwards, which leads to shrinkage deformation. And the same thing you can understand from this figure also. Like there is one hydration product, meniscus has formed due to evaporation, and it is causing shrinkage, inward pulling force. Okay, which will lead to shrinkage of the entire system. Okay, so this is how shrinkage deformation, if in the simplest of manner, if I will try to explain, this is the basics behind the shrinkage in concrete. Now on this slide, like there is just a summary of broad areas of like different aspects of concrete and environment and how they affect shrinkage. So it is known that smaller pores, they create a higher capillary pressure, so they can cause more shrinkage. So shrinkage is more in smaller pores rather than in larger pores. If there will be higher evaporation, there will be greater surface tension, so there will be more shrinkage. That is again a commonly known phenomena. More hydration will cause more bound water, so there will be more internal shrinkage, that is due to autogeneous shrinkage. Low RH will lead to faster evaporation, then it can lead to higher drying shrinkage, that we also know now. And more CO2 exposure will lead to more carbonation shrinkage. So these are like some of the commonly uh, known aspects of concrete on how they affect the shrinkage. Now, if we particularly go to the concrete part, how concrete affects the shrinkage rate. So, as the aggregate content increases, it reduces shrinkage. Why? Because aggregate is the rigid skeleton. It will restrict the shrinkage by reducing the paste volume. So, more aggregate means less cement paste, so it will reduce the shrinkage. Now, water to cement ratio. More water will lead to increased capillary porosity, and if there will be increased capillary porosity, it will be more susceptible for moisture loss, and so more will be the shrinkage. Curing condition. If the curing condition is poor, then the strength development in concrete will be poor, and it can lead to rapid moisture loss from concrete. Okay, and this will lead to higher shrinkage in concrete, while proper curing will reduce the shrinkage effect. Relative humidity, as we have seen, in dry condition moisture evaporates faster than in concrete, so it will cause higher shrinkage. So lower humidity increases the shrinkage. Volume to surface area, so again similar to creep, if the surface area is more, the chances of water evaporation from concrete will be more, so lower volume to surface area ratio increases the shrinkage. Slump. Higher slump means more water has been used in concreting, so if there will be more water used in concreting, then there will be more shrinkage. Fine aggregate to total aggregate ratio. So the fine aggregate, if there is more fine aggregate, it means there will be more cement content in concrete. As if there will be more cement content in concrete, then there will be chances of higher shrinkage in concrete. So like again similar to creep, it is not the aggregate that causes shrinkage, it is the cement paste that is causing the shrinkage. Okay, air content. Higher air content will reduce the shrinkage effect because it will provide space for stress to get relieved inside the concrete. Okay, so it will reduce the shrinkage effect. However, if there will be excessive air, we can compromise on strength. So it has both positive and negative effect, air content. And more cement content will reach to increased shrinkage because of autogeneous shrinkage or plastic shrinkage or drying shrinkage chances. Okay, so this is how different factors of concrete, different concrete properties can affect the shrinkage. Now, how we can predict shrinkage? It is completely similar to what we have seen in creep. So again, we have a ACI code. and which predicts shrinkage strain after time t naught. Suppose at t naught shrinkage starts, so after time t how much shrinkage will be there, we can give see from this equation. So s infinity into t minus t naught upon a plus t minus t naught. So this a factor will change. For moist curing it is 35, for steam curing it is 55, and S infinity is the ultimate shrinkage. So this is determined again by this equation where there are seven factors related to different properties: curing, RH, volume to surface area ratio, slump factor, fine aggregate, cement content, and air void content. So how we determine this different factors? We have different relationships available. Okay, so based on this different relationship, like this is for K1, this is for K2, K3 we have this relation, for K4 we have relation, certain relation, for K5 we have certain relation, for K6 and K7 we have certain relation. For all these factors there are certain set of experimental relationships that has been determined. So using, if we know the environmental and the material property, we can determine all the six factors, and once we determine all the six factors we'll know the ultimate shrinkage value, and then we can determine the predict the shrinkage in concrete after some time t. So it's just similar to what we discussed for creep. And then again similar to creep, there is BS method also, which predicts shrinkage after 6 months and 30 years. Okay, so you can see here, based on volume to surface area ratio, different volume to surface area ratio, and average relative humidity, and we can predict the shrinkage chain. Okay, so if I know the relative humidity, I can predict what will be my shrinkage strain after 6 months and after 30 years. Okay, so this chart was developed for a water to cement for 190 liter per meter cube water. Okay, so for other water content, they have given a certain equation that you can that one can use to determine the to predict the shrinkage. Now the prediction was for part was the same as we have seen for concrete, so that's why I've moved quickly through that part. Now on this slide I have few measurement of shrinkage in concrete that we performed in laboratory condition. How we measure shrinkage in laboratory condition? So in the first two image you can see the setup of length comparator. Okay, where is my cursor? Okay, here. So this is known as length comparator, which is based on IS 49459. So how shrinkage is determined here? So in this, a concrete prism sample is cast and cured under standard condition first, and after a curing period, its initial length is determined. So you can see this is a prism sample, and its initial length we will determine using the length comparator. So this is a length comparator. Okay, we determine the length of the sample. How? So there are two anvils like gauges that are inserted at the top and the bottom. So these are like metal gauges that are present at the top at the bottom, and using those we compare estimate the length of the sample. This is the initial length. Now I will expose this sample to drying condition, and then I will periodically measure the change in length over time. Okay, so I can determine shrinkage change as the shrinkage strain as change in length upon original length. Okay, so that will give me the shrinkage in concrete. So this is for using length comparator. Okay, and this gives me drying shrinkage, because once my concrete has hardened, then I am determining the shrinkage. So this will give me the drying shrinkage in concrete. In this second image, the okay, this third image, okay, you can see ASTM C1608 setup. Okay, and this is used for autogeneous shrinkage. Like initially, when cement hydration occurs, the autogeneous shrinkage or chemical shrinkage that is occurring in concrete, we determine it. So how we determine? So here you can see there is a sealed sample. So this is my cement paste. Okay, and this is my tube, some glass beaker or tube, over which a rubber cork is fitted, and there is one capillary tube, okay, which is passed through this cork, and at the top of the capillary tube I have oil, so that there is no warm moisture evaporation due to temperature outside. Okay, now here what happens, since my sample is sealed, okay, there will be no moisture loss from inside. However, If the cement hydration will occur, its volume will decrease. So as the volume will decrease, I will see the loss of water drop in this. I will see a drop in water level in this capillary tube. So the change in volume we can measure by this movement of fluid in this capillary tube, and that will be due to the autogeneous shrinkage of my cement paste. Okay, so this is performed as per ASTM C1608 part 7. And finally, there is ASTM C1581, a ring test, restrained ring test, to evaluate the shrinkage induced cracking in concrete. Okay, so in this method, what is there? There is a concrete ring which is cast around a steel ring. So you can see there is a steel ring, okay, around which I have casted the concrete. Okay, so we have created a internal restraint as the concrete shrinks. Okay, now as the concrete undergoes drying shrinkage, what will happen? Tensile stresses will develop due to this restraint effect of ring. Okay, you can see this. There is a ring. Okay, there is a concrete sample, there is outer ring and there is inner ring. Okay, now as shrinkage happen, there will be tensile stresses that will be generated over time, and a strain gauge we will apply to measure the tensile stresses that is generated in the steel ring. Okay, and that will give us the idea of the shrinkage in concrete and how it will exceed the tensile strength of concrete. Okay, so this is known as the ring test for calculating restraint shrinkage. Okay, mostly we use this setup and this setup for autogeneous and drying shrinkage. We have these two test setups that is commonly used in laboratory practice. Okay, and finally, how shrinkage affects concrete, we can see from this diagram. Okay, so there can be multiple types of cracking that can occur. Mainly the cracking due to shrinkage, these are minor cracking that occurs. Okay, and you can see here in location D, E, and F, some minor cracking that are observed due to moisture loss in concrete. And these are primarily due to the shrinkage in concrete. Okay, so this was all from the today's week. So first we discussed modulus of elasticity. We discussed various factors affecting modulus of elasticity and various measurement. We talked about fatigue and bond strength, and we discussed about creep and shrinkage in concrete and different points related to them. Okay. So like now, if anyone has any doubt in the last part of the discussion, that is shrinkage, they can ask. Let me stop the recording.